Hello. Okay. In the previous class, we discussed different types of the addressing modes. Okay, it's completed. Then we completed program control in tms320c54xx processor. Okay, and today we'll discuss uh, pipelining of pipeline operation of tms320c 54xx processor. How? What is meant by the pipeline operation? Anybody? Anybody familiar with pipeline operation? The CPU of 54xx devices has a 6-level deep instruction pipeline. The 6 stages of the pipeline are independent of each other. This allows overlapping of execution of instructions. Okay, during any given cycle, up to 6 different instructions can be active, each at a different stage of processing. The 6 levels of the pipeline structure are program, prefetch, program fetch, decode, access, read operation, and execute and write operation. Okay, here we classified the pipeline operation as 6 stages: prefetch, fetch, decode, access, read, and execute a write operation. Okay, briefly we'll discuss here 6 stage of pipeline operation of the tms320c54xx processor. Okay, there are 6 stages. Okay, what is meant by the pipeline? Parallel execution of the instructions. Okay, first we will discuss during program prefetch, the program address bus, that is PAB, is loaded with the address of the next instruction to be fetched. Okay, the program address bus is loaded with the address of the next instruction to be fetched. That is the operation of the program fetch. Then next phase is fetch. In the fetch phase, an instruction word is fetched from the program bus. Okay, the instruction can be fetched from the program bus. Okay, and loaded into the instruction register, that is IR. Okay, these two phases form the instruction fetch sequence. Here we can fetch the instruction. Okay, next one, third one, decode. During the decode stage, the contents of the instruction register IR are decoded to determine the type of memory access operation and the control signals required for the data address generation in it and the CPU. Okay, in decode phase, what we can do? The contents of the instruction register are decoded to determine the type of memory access operation and the control signals required for the data address generation in it, okay, and the CPU. Here we can decode the instruction. See here, loads IR with the contents of PB, decodes the IR contents. Okay, that is about the decode stage. Next, what is the next stage here? Next stage is access. Okay, see here. The access phase outputs the read operands address on the data address bus DAB. If a second operand is required, the other data address bus CIB is also loaded with an appropriate address. Auxiliary registers in indirect addressing mode and the stack pointer are also updated. in the access space. What we can do here? The outputs of the read operand address on the data address bus DAB. If a second operand is required, the other data address bus CAB is also loaded with an appropriate address. Okay, and auxiliary registers in that addressing mode and stack pointers are also updated after the execution. Okay, after the operation of this one, what will happen? The auxiliary register values. Okay, that location address and stack pointer also updated. See here in access mode, what we did? Loads DAB with a data 1 read address. If required, loads CAB with the data 2 read address. If required, updates auxiliary registers and stack pointer. Okay, in DAB is loaded with data 1 read address. Operand 1 read address. CAB, if two operands are there, then CAB is loaded with data 2 read address. Okay, if required, update the auxiliary registers and stack pointer. Okay, that is access phase. Then in the read phase, the data operands, if any, are read from the data buses DB and CB. This phase completes the two-phase read process and start the two-phase write process. The data address of the write operand, right, any, is loaded into the data write address bus, that is EAB. So here two operands are accessed. That means here two in the read phase, the data operands, if any, the read from the data buses DB and CB. Here in access phase, the here mentioned loads the DAB with the data 1 read address, okay, and CAB with the data 2 read address. Then here we can read the data from the data bus DB and CB bus. See here, given. If any are read from the data buses DB and CB. This phase completes the two-phase read up process and starts the two-phase write process. Here we read the two operands. Okay, the data address of the write operand, if any, is loaded into the data write address of the EAB. Okay, the last one is execute operation. Execute phase. Executes the instruction and loads the EB with write data. Here write address in the EAB. Okay, the execute phase writes the data using the data write bus EB and completes the operand write sequence. Okay, the instruction is also executed in this phase. Okay, just remember this table. In pipelining of tms320c54xx, which has 6 stages: pre-fetch, fetch, decode, access, read, and execute/write. In pre-fetch, the PAB loads the PAB with the PC contents, which the next instruction to be fetched. PAB, program address bus, is loaded with the next instruction to be fetched. Okay, then fetch here, the PB is loaded with the instruction word. Here you can fetch the particular instruction. Then decode, whatever the data stored in the instruction stored in the IR register, that can be decoded. Then access, here the DAB and CAB are loaded with the read addresses. That operand 1 address, operand 2 addresses. Then here read, here we can read the two operands. loads DB with the data 1 read operand, loads the CB with the data 2 read operand. Okay, then loads the AB with the write address. Okay, then executes the instruction and loads EB with the write data. Here we can do the write operation after the execution. Just remember this table, okay, 6 stages of the pipeline operation of the tms320c54xx processor. Then this is the explanation. Okay, please go through this. It's very important. Okay, now here we discuss one example here. Show the pipeline operation of the following sequence of instruction if the initial value of AR3 is 80 and the value stored in memory location 80, 81, 82 are 1, 2 and 3. Okay, here this is the instruction: load star ARP plus comma A, add operation slash 1000H comma A, store lower value of the accumulator in AR3 registers. Okay, see here. There are 6 stages here: prefetch, fetch, decode, access, read, write. Okay, first here we can load the LD, prefetch, LD. Okay, then ARP context is 80H. Then add LD, add LD. After this add, STL will be accessed. See, parallel execution, STL, add and load. See here, this LD go for the decode operation. Okay, add is fetched here and prefetch is stored in the program bus, STL. Then this STL move to fetch operation, add is moved to decode operation and load is moved to access. Here you can read, here access means where you can read the, here get the operand 1 address. Okay, see LD 81. Now you can read the next address data 81. Okay, STL move to decode, add move to access, okay, and LD move to read process. 81 is loaded with the value 1. Then STL move to access operation. Here add operation is processing, load the value 82. 81 and 82 is loaded. Then you can do the addition. Store lower value of the add and okay, STL and add. Loading is over. Now you can do the addition, store the value and adding. Okay, 82. Okay, 82 is, that means location. See here. Memory location 80, 81, 82 are loaded 1, 2 and 3. Okay, so 82 is, can add it here 1 and 001H, then we will 1001H and store the lower value, that is 1001H. Please practice this example, it's very important. Okay, prefetch, then again add is prefetch and LD is fetched. That means LD is stored in the instruction register. Then it go for the decoding process. Then it go for the accessing process. Then it's read process, write process. Again add, the prefetch, fetch, decode, access space. Okay, then STL, prefetch, fetch, decode, access, read operation and execute and write operation. Okay, please go through this and go through this example. It's very important. Okay. Similarly, one more example here. Show the pipeline operation of the following sequence of instruction if the initial values of AR1, AR3, AR 84, 81 and 1 and the values stored in memory location 81, 82, 83, 84 are 2, 3, 4, 6. Also provide the values of registers AR3, AR1, T and accumulator. A after completion of each cycle. See here. First add, okay, then load instruction, next MPY instruction, then add instruction. See. Okay, here the AR3 register AR1, A and T. Here during the add operation, AR3 is loaded by 81, AR1 84. AR3 right? AR3 is loaded by 81. Yes, AR3 is loaded by 81 and AR1 is loaded by 84. Check it. See 84. See. And accumulator loaded by 1. Accumulator loaded by 1. Then load LD will be accessed. The address of the LD is stored in free patched. That means it's in program bus. Then add is go to fetch. That means this is add is stored in the instruction register. Okay. Same data will continue here. MPY LD add 81 84 1. Okay. During the access process it will happen. Okay. Here add same add MPY LD add. Okay. Now the data will be 82. AR1 becomes 85 and A value is same 1. Then add goes to decoded. MPY will access KLD and add. Okay, just go through this here. Okay, otherwise you can please practice this problem. So many times they ask this question. Okay, pipeline operation of this instruction, this code. Okay, it's very important. And this is the pipeline operation of this code. Please practice it. How the data is accessed here. How it can changes. How the data is updated. Okay, and please go through this stages: refresh stage, fetch stage, decode, access, read, and execute and write operation. They ask the question. Briefly explain pipelining operation of tms320c 54xx processor. Okay, please go through that. And next one is memory space of tms320c 54xx processor. Memory space of tms320c 54xx processor. Here, tms320c 54xx processor provide for a total of 128K words of memory extendable up to 8192K words. Okay, the processor provide a total of 128K words of memory. This can be extendable up to 8192K words. This includes both program memory and also a data memory. Okay, within this space, RAM. Okay, here the RAM can be single access and also dual access RAM. Okay, here dual access of 2 read operation, single access, one read operation, one write operation. Here 2 read operations, 2 write operations at the same time. Then ROM, EEPROM, or memory mapped peripherals may reside either on chip or off chip. Okay, here the memory space which consists of 128K words. That memory can be extendable up to 8192K words. Okay, here this which includes both program memory and data memory. Okay, within this space which consists of RAM memory, ROM, EEPROM, okay, and also memory mapped registers or peripherals, which can be either on chip or off chip. The program's memory space is used to store program instructions and the tables used in the execution of program. Program memory means which can store the program instructions. Data memory means it can store the data. Okay, see here, the data memory space is used to store data required to run programs and for extra memory map peripherals. Okay, this is the data memory. Data stands for data memory here. Memory map registers. It consists of sketchpad RAM, on-chip DA RAM, okay, and on-chip DA RAM 4. When DRAM equal to 1 and DRAM equal to 0. Okay, these are the program memory. Page 0 program, page 0 program. See here, all this is reserved when OVLY equal to 1 and external OVLY equal to 0. Later we'll discuss about that with example. See here, there are two modes here, microprocessor mode and microcontroller mode. When MP bar MC bar equal to 1, okay, it's in microprocessor mode. When MP slash MC bar equal to 0, it's in microcomputer mode. Later we'll discuss some examples on that. Okay, the size of the data memory is 64K words, part of which is on-chip DA RAM, dual access RAM. The size of the data memory is 64K words. Okay, in that, some part can be used as on-chip DA RAM. The device automatically accesses the on-chip RAM when the address is within its range. Memory map registers are also part of the data memory space. Okay, then the program memory is organized into 128 pages, each of 64K word size. Page 0 is part of the basic 128K space, and pages 1 to 127 are extended pages. Okay, out of the 64K words on page 0, in that 4K words are on chip ROM. Okay, the page 0 is part of the 128K space. Okay, pages 1 to 127 are extended pages. Okay, yeah, out of 64K words on page 0, in that 4K words are on chip ROM. The remaining space on page 0 as well as extended space consists of DA RAM and SA RAM, dual access RAM, single access RAM, both on chip and off chip. Okay, the 4K on chip ROM space contains a GSM AFR speech code codec table, a boot loader, MULA and ALA expansion tables, and sign lookup table, and an interrupt vector table. Okay. The MP/MC bar OVLY DROM bits located in the processor mode status register are used to enable and disable on-chip memories in the program and data spaces. See here, the PMST, the processor mode status register, which consists of MP/MC bar, OVLY, and DROM bits located in the processor mode status register, PMST. Okay, these are used to enable or and disable on-chip memory in the program and data spaces. Here we'll check it. I will show the PMST. See here. processor mode status register of tms320c 54xx processor. So it consists of RPTR, okay, MP/MC bar, OVLY, APIS, DROM, CLK of SMUL, SSD. Okay, these MP/MC bar, OVLY, and DROM, these are used to enable or disable the on-chip and off-chip memories. See here, enable and disable on-chip memories in the program and data space. Okay, what is the function of these bits in the PMST register? Program mode status register. Here I will, in table they given here. Yes. You can access, enable or disable the on-chip memory configuration, right? MP/MC bar, when this bit in PMST is 0, then ROM is enabled. When this bit is 1 in PMST register, then ROM not available. OVLY bit in PMST register is 0, okay, RAM in data space. RAM in, where it is, it's in data space. When OVLY equal to 1, RAM in program space. Okay, next one is DROM. DROM means when it is 0 in PMST register, ROM not in the data space. When DROM equal to is 1 in PMST register, then ROM in data space. It's very important. Please go through this table. This table is very, very important. Okay, when it is 0, what will happen? When it is 0 and 1, okay, what will happen? Okay, just remember, MP/MC bar equal to 0, ROM is enabled. When it is 1, ROM not available. When OVLY equal to 0, RAM in data space, and it's in 1, RAM in program space. When DRAM equal to 0, ROM not in the data space. Okay, when it is 1, ROM in the data space. Very important, please go through this. If they ask any problem on this, okay, this table is very important. Okay, I'll show you here. Then see here. When MP/MC bar equal to 1, okay, we call this one as microprocessor mode. Microprocessor mode. When MP/MC bar equal to 0, it's in microcomputer mode. Okay, and also refer MP/0. If it is 0 means ROM is enabled, means here, see, on-chip ROM is enabled here. ROM is present. Okay, here there is no ROM. ROM is disabled. See here, when MP/MC bar is 1, it's ROM not available. See here, ROM is not available. Okay, here ROM is available. On-chip ROM is available. Okay, just remember the address. Okay, this is not necessary. If you want, you can practice it. That 0000 H2 FFFH 00H2 007F is reserved. When Y will equal to 1, it's reserved. Y will equal to 0, it's external. Then 00802 7FFF on chip DRAM. When Y will equal to 1, otherwise 0. It's, when Y will equal to 0, it's external. Okay, external purpose here and interrupts. Here reserved and external same addresses here 000h to 007h. Okay, one example we will discuss here. What is the configuration of on-chip DRAM, on-chip DRAM, on-chip SARAM and ROM if MP/MC bar equal to 0, OVLY equal to 1 and DROM equal to 0. See here, MP/MC bar equal to 0, MP/MC bar 0 means ROM is enabled. Okay, OVLY equal to 1, that means RAM in program space. RAM in program space. Okay, then DRAM equal to 0. DRAM equal to 0 means what will happen? ROM not in the data space. See, I'll go through the explanation here. When MP/MC bar equal to 0, okay, 0 means where? Here. It's in microcomputer mode. Microcomputer mode. Then 16K on-chip ROM is enabled as program memory at address C000H2 FEFFH. C00H2 FEFFH. When, okay, see here. When MP/MC bar equal to 0, 16K on-chip ROM is enabled. Yes, there in the table they given. When MP/MC bar is equal to 0, ROM is enabled. Okay, 16K on-chip ROM is enabled as program memory at addresses C000H2 FEFFH. See, C000H2 FEFFH. 16K watts of ROM on-chip ROM. When MP/MC bar equal to 0, ROM is enabled. Okay, next, OVLY equal to 1. OVLY equal to 1. 1 here and 1 here. When OVLY equal to 1 means on-chip DRAM here equal to 1, DRAM is mapped onto the program memory space at address 0080H2 7FFF here 7FFH. Memory at addresses 00H to 007FH is reserved for memory map registers and scratchpad purpose. Here on-chip DRAM here 0080H to 7FFH. Okay, see here it can be mapped onto program memory space. DRAM is it's in data space. Okay, DRAM is mapped onto the program memory space at addresses this one. Okay, and the address is 00H to 007FH in the data memory. You can check it 00H to 007FH up to here memory map registers and scratchpad RAM. Therefore, the memory map registers and scratchpad purpose. Since DROM equal to 0, okay, ROM is not mapped onto the data memory. Here, DROM equal to 0, ROM not in the data space. ROM is not in the data space. You can use the external ROM memory. Okay, external, when DROM equal to 0, you can use the external ROM. Okay, similarly, one more example here is given. MP/MC bar equal to 1, OVLY equal to 1, and DROM equal to 1. MP/MC bar equal to 1 means, so what is the here? ROM not available. And also it's in microprocessor mode. It's in microprocessor mode. Then OVLY equal to 1. Since OVLY equal to 1 means DRAM is mapped onto the program memory space at address same here. And Memory at address is 00H2 007FH is reserved for memory map registers and scratchpad purpose. Here they given 000H2 007FH is used for memory map registers and scratchpad RAM. This can be reserved for that memory map registers and scratchpad RAM. And DROM equal to 1 means 16K ROM is mapped onto the on-chip data memory at address C000H2FEFFH, and memory from FF00H2 FFFH is left for reserved purpose. Okay, some external purpose you can use it. So here FF00H2 FF7FH is reserved. Okay, and here the ROM is mapped onto the on-chip data memory at address C000H2 FEFFH. Okay, this is about the memory space of tms320c54xx processor. Okay, this completes module 3. Okay, and please write